Okay, we are starting logarithms today, which you will find, sorry, I'm fixing this, you will find are no big deal. So let's go back and look at a couple things from the function unit. Recall a function which has notation f of x, has an inverse, f inverse of x, if and only if f of x is 1 to 1. Which means it passes the horizontal line test. To find the inverse of a function, remember we switch x and y. We switch x and y in the equation. We can switch x and y in the table of coordinates. And when we switch x and y in the equation, we end up solving for y. The graph of an inverse function, so we've got how to write the function here, how to get the table of coordinates here, and then what the graph should look like. The graph of an inverse function is a reflection of the function graph over the line. Do you remember? Y equals x. So they're reflections of each other over the line y equals x. So let's go back to exponentials, and here we have y equals 2 to the x. You can put that in your calculator if you want. We're going to graph it here on this grid. Label your axes. I don't need to put this in my calculator. I'm going to do it in my head. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. And the negative exponents, 2 to the negative 1 is a half. 2 to the negative 2 is 1/4. 2 to the negative 3 is 1/8. I'm going to need that skinnier pen. The domain of this function, well, that's your x values, remember. What can we put in for x? And that answers all reals. And look at your y values. They're going to get increasingly larger this way. And going in the negative direction, you get smaller and smaller fractions. But think about the value you will never hit. All your y values will always be greater than 0. So let's graph this exponential function. Pause your video if you need to take a little more time to graph this. That's okay. And let's see, exponential growth. And let's label it. Terrific. That's an exponential function. Now, what we set up above was if we switch our x and y columns, then we'll get a plot for the inverse. So this graph over here, this table is going to represent f inverse. And you can see for negative 3, I put it in the y column. So the x column is 1/8. And I'm just going to copy this y column all the way down. For negative 2, I have 1/4, negative 1, 1/2. Instead of 0, 1, 1, 0. Instead of 1, 2, 2, 1. Switch 2 and 4. Switch 3 and 8. What else switches? If we've switched the x and the y columns, then we're actually switching our domain and range. So our new x values here are all greater than 0. Our new y values here are all reals. So these switched as well. So let's plot these points for the inverse function. I'll do those in red. Over 1/8 down 3. Over 1/4 down 2. Pause it if you need to. Over 1/2 down 1. Over 1, 0. And we'll connect these dots, being careful. And we have the inverse function. So how do we label it? Well, we set up above that if we take the equation and switch the x and the y, then we get our inverse graph. So that's okay for now. But what we're going to learn today is what the y equals form of this is. Okay? So there's a graph. We're going to try another one. If you'd like here, pause the video and graph y equals 3 to the x over the set of this domain, knowing we can put in any real value and knowing that we will get out all our y's greater than 0. Go ahead and pause, get some values for your y column, and let's see if our graphs match up. I'm not even going to try and graph 327, and it actually gets real close. -2, 1/9, and -3, 1/27. With the precision we have, that's not reasonable. So this exponential graph, y equals 3 to the x, rises much more quickly. It's steeper because that base of 3 is so much bigger. Awesome. Let's switch x and y now. And let's switch each of these points. I'm just copying into the x column exactly what I see in the y column. Easy peasy lemon squeezy. Also, we know the domain of our function becomes the range of our inverse, and the range of our function becomes the domain of our inverse, but we need x's are greater than 0. Okay. I'm going to plot this one in green. Over 1/27, kind of impossible, but way down here at 3. Over 1/9, -2. Over 1/3, -1. 1, 0, of course. 3, 1, 4, 5, 6, 7, 8, 9, 2. And we run out of real estate here. Do not cross that y-axis here. Be real careful. I'm not crossing this y-axis. And I will label this today, x equals 3 to the y. Beautiful. So if you didn't get that graph when you tried this on your own, you probably need another example. And I can certainly give you one of those in class. Just ask me. So what did we just do? What you just did is you graphed your first logarithmic function. Congratulations. A logarithmic function. So they're not that scary. They're just the inverse of an exponential function. So the inverse of a exponential function is a logarithmic function. we started with f of x equals 2 to the x, which is the same as y equals 2 to the x. We switched our x and y to get the inverse. So what you need to learn now is how to write this as a logarithmic function. Y is the exponent here. So we say y equals the log base 2 of x. And this 2 is a subscript. If I had a line on my paper, all of this would be on the line, and the 2 would be a subscript below the line. So our inverse function then is log base 2 of x. The base comes from this number. The x comes from what the other side is. So let's work with this. Let's work with going back and forth. This here is just a progression through the language and the vocabulary. If you want to remember the phrase, logarithms are exponents. Notice up here, the exponent y equals a log. So logs are exponents. The exponent equaled a log. So this is just a progression through that language. Let's see what we have. We started with x equals 2 to the y. So I might say y is the exponent. That's true. For a base of 2, that's true. That equals x. That's true. Then knowing the phrase logarithms are exponents, all I do in the next one is change the word exponent to logarithm. Y is the logarithm for a base of 2 that equals x. And then we remember if we say y is, that's the same as y equals. So we change y is the logarithm to y equals the logarithm. And then we add in the other two parts. Y equals the logarithm for a base of 2 of x. You can say y equals log base 2 of x. What you really need to be good at, and we're going to practice this a lot, is knowing that this x equals b to the y can be rewritten as y equals. So there's your exponent. Exponents are logarithms. Logarithms are exponents. What's our base here? B, subscript, and then that equals x. So y equals log base b of x. That's how you say that. So we're going to practice quite a bit making this transition, taking something in this exponential form and putting it in logarithmic form. Okay? So each of these sections now should correspond with a section on homework. At any time, stop the video and try one on your own. And then start it up and see if you got it right. You'll know if you've got it. So first, for each of these functions, I'm writing an equation for the inverse. So remember, to write an inverse, we switch x and y. And then we solve for y. So this is y equals 3 to the x. This is y equals 5 to the x. This is y equals 3/2 to the x. This is y equals square root of 2 to the x. So let's start our inverse work. Switch x and y. Then solve for y. Let me get rid of this here. It's just in my way. Y equals, so exponents equal a logarithm with that base of x. And there's your inverse function. This function and this function are inverses. Let's try number 2. Switch x and y. Now rewrite it in its y equals form. The exponent equals the logarithm base 5 of x. So y equals log base 5 of x is the inverse of y equals 5 to the x. Now this one, number 1, this one you graphed. You graphed this on the first page, and you graphed its inverse. So let's go back and relabel the graph. I think it's on page 2. There we go. So this graph that we had originally labeled, x equals 3 to the y, is the same as y equals log base 3 of x. And like I said before, you had graphed your first logarithm equation. All right, we're still writing inverse functions. Maybe stop and try this one on your own. Switch x and y. Rewrite it for y. And you're good. Switch x and y. Rewrite for y. And you're good. All right? Let me know in class tomorrow if you need more examples of writing an inverse function. Letter B. These say solve for y. So if you notice in each of these questions, y is the exponent. Actually, here it doesn't look like it, but we can rewrite this. That didn't come out quite right. Oh, no, I'm sorry. Number 4 is completely different. Whew, glad I double-checked that. Okay, so solve for y. Y is the exponent. That means it equals a log. Base 6 of x. Try number 2. Y is the exponent. That means it equals a log. Base 10 of x. This time we have negative y is the exponent. So negative y equals log base 12 of x. But we don't leave negatives in front of our y's, so we end up with y equals negative log base 12 of x. All right, these are a little different because I actually have a logarithm question written here. So let's see what we can do. Do you know when you look at this what the base is? Do you know when you look at this what the exponent is? That can get a little tricky because you don't have one that's obvious. And do you know when you look at this what the number is? So I'll start with the base. I think it's the easiest to pick out. 2 is the base. The exponent? Well, we said logs equal the exponent. Here's the log, and it equals x. That means x is the exponent. And then the only one left is y. The only expression or part left is y. So what we have here now is a base of 2, an exponent of x, and that should equal y. So there's your equation, put back in y equals form. That one was a little different. Let's try another like that, number 5. When you look at this, we're going to rewrite it back in exponential form. So notice in number 4, this was in log form. We rewrote it in exponential form. Up above, we did the opposite. So we have log form again. So the base in number 5 is 8. I hope you're answering. The exponent is x, because the log equals the exponent. It's right here, logs are exponents. You can change that to logs equal exponents. And then the number is y. So rewriting this in exponential form, we get our base 8 to our exponent x equals y. Or of course, y equals 8 to the x. Okay. So solving exponential or logarithmic equations can be simplified by rewriting the equation in its equivalent log or exponential form. You want to be able to go back and forth, and we actually just tested that. So we know that any number equals a base to an exponent. That can be switched around to the exponent equals the log of a base of the number. So we shorten this with a little n for the number, a b for the base, and an e for the exponent. So you end up with the exponent equals log base b of n. And that's written down here below. You want to be very good at going from exponential form to logarithmic form. You're really just rewriting the problem to help you solve the problem. So let's see what we have on the next page. I think we ended. I think we're good. Let's see. Let me give you one example down here, 1 or 2. We know that 2 cubed equals 8. So if I wanted to rewrite that in logarithmic form, okay, 2 is my base, 3 is my exponent, and 8 is my number. So putting this in logarithmic form, I'd say my exponent equals the log base 2 of 8. Let's do one more, then we're done. 25 to the half power equals 5. Put that in logarithmic form. The exponent equals the log base of 25 of 5. We'll get lots more practice with that in 8.2. I'll see you tomorrow.